Hey there! Do you have problems with logic and reasoning?
Worry no more, we have the most basic tips and tricks for you.
In this video, we will tackle logic and reasoning as discussed on Module 2 of our Math 10 class. If you are ready, buckle up and come explore the world of
Logic and reasoning with us.
We begin by learning a very simple topic in the fields of mathematical logic, statements, and connections. How do we define mathematical statements? Mathematical statements are usual declarative sentences used in math and are assigned with truth values, either true or false. Questions, exclamations, and imperatives are not considered as mathematical statements as well, since these sentences do not have a truth value. Let's take a look at some examples. The following are not mathematical statements. Numbers 1 and 2 are not mathematical statements since they are not declarative sentences and they do not have a truth value. Numbers 3 and 4 are not mathematical statements because they do not have a clear meaning or value. Lastly, number 5 is not a mathematical statement. Why? Because 13 is not everyone's unlucky number. For one, it is their unlucky number, and for the other, it is not. So it does not have a clear value. Mathematical statements cannot be both true or false. It cannot have both values. Let's move forward to the negation of statements. Negation is simple as contradicting what is stated. We add the word not to negate sentences. Let's take a look at some of the most common negations. First, the negation of A or B. Consider the statement, you are either sad or happy. For this statement to be false, you can't be sad and you can't be happy. In other words, the opposite is to be not sad and not happy. Or if we rewrite it in terms of the original statement, we get, you are not sad and not happy. Second, the negation of A and B. Consider the statement, I am both sad and happy. For this statement to be false, I could be either not sad or not happy. If we let A be the statement, I am sad, and B be the statement, I am happy, the negation of A and B becomes, I am not sad or I am not happy. Or, not A or not B. Third, the negation of if A then B. Consider the statement, if I am sad, then I am happy. For this statement to be false, I would need to be sad and not happy. If A is the statement, I am sad, and B is the statement, I am happy, then the negation of A then B is I am sad equals A and I am not happy equals not B. How about negating the statements with quantifiers? How is this performed? We negate sentences not only by using the word not. There are these quantifiers all, some, and none, also to negate statements. Let's take a look at some examples. First, the statement, all students recycle paper. The negation of this statement is simply some students do not recycle paper. This is also equivalent to not all students recycle paper. Second, the statement some of us will graduate. The negation of this statement is simply none of us will graduate. Third, the statement no students are unreliable. The negation of this statement is simply some students are unreliable. Do you find it hard? Don't worry, since these ideas can be remembered by using the square of opposition. The negation of all is diagonally equivalent to some are not. The negation of some are is diagonally equivalent to no or none.
In this section, we will introduce what is perhaps the most confusing part of logic and reasoning, the truth tables. Mathematics normally uses a two-valued logic. Every statement is either true or false. You use truth tables to determine how the truth or falsity of a complicated statement depends on the truth or falsity of its components. Complex, compound statements can be composed of simple statements linked together with logical connectives, similarly to how algebraic operators like addition and subtraction are used in combination with numbers and variables in algebra. Independent, simple components of a logical statement are represented by either lowercase or capital letter variables. These variables are independent in that each variable can be either true or false independently of the others. A truth table is a chart of all the possibilities. To determine the number of rows a truth table should have, we use the following formula. So for example, if we have two variables, let's say P and Q, our table would look exactly like this. On the other hand, if we have three variables, our table would look like this. This process increases exponentially for every variable that we add to the table.
In order to uncover the truth value of a compound statement, something called logical connectives or operation in statements are used. The 5 logical connectives are: first, conjunction; second, disjunction; third, conditional; fourth, biconditional; and fifth, negation. A conjunction is represented by a mathematical symbol that looks like an upside-down V and is read as P and Q. The statement is true only if both P and Q are true. Anything else is false. A disjunction is represented by a mathematical symbol that looks like a V and is read as P or Q. The statement is true if either P or Q are true, but if both are not true, then it is false. A conditional is represented by an arrow pointing to the right and is read as P then Q. In a conditional statement, the letter P is the premise and the letter Q is the conclusion. A conditional statement is false only when the premise or P is true and the conclusion or Q is false. Any combination is considered true. A biconditional is represented by an arrow that is pointing simultaneously to the left and to the right. It is read as P if and only if Q. The statement is true if P and Q will show both true or both false. Otherwise, it is false. A negation is represented by a mathematical symbol that looks like a tilde. It is the only non-binary operation or logical connective because it entails only one statement. It reverses the truth value of the statement from true to false and vice versa. The conditional is something that we encounter on a daily basis in the form of daily decision making. For instance, if it rains today, then one would consider not walking to school, or one might not even go to school at all. A statement is conditional because it depends on the premise in the formation of a conclusion as much as we depend on conditions to make an informed decision.
Similar to Venn diagrams, Euler diagram is a diagrammatic means of representing sets and their relationship. Its purpose is to create a visual representation of logical arguments as a mean to evaluate the validity of given conclusion. Consider the statement, carbonara is a pasta. The statement suggests the inclusion of carbonara as an element of the set pasta. Therefore, we can create an Euler diagram out of this representation by drawing a circle to represent the set of pasta and let x represent the element carbonara. Quantifiers. In the Euler diagram, we have quantifiers all, some, and none. The first one is the all quantifier. Consider the statement, all cakes are sweet. There are two sets in this statement. First, the set of cakes, and second, the set of sweet things. So let's represent them by circles. Since all cakes are sweet, this automatically puts the set of cakes inside the set of sweet things. The second quantifier is some. The some quantifier signifies the inclusion of only some elements of the set. Consider the statement, some noodles are spicy. Since we have two sets that are intersecting, there must be a region where some elements are shared by the two. Thus, we draw this kind of statement as follows. The last quantifier is the no or none. The non-quantifier means that the two sets are mutually exclusive of one another. Thus, we draw these sets apart from each other. Consider the statement, no cakes are spicy.
Other than Euler diagrams, we can also test the validity or invalidity of an argument using inductive or deductive reasoning. Inductive reasoning is the process of reasoning from specific instances to a general statement. For example, adobo is delicious. Sinigang is delicious. Kare-kare is delicious. Therefore, all Filipino dishes are delicious. Deductive reasoning, also called logical deduction, is the process of reasoning from a general statement to a specific instance. For example, all UP students are smart. My friend is a UP student. Therefore, my friend is smart. In this video, we taught you various ideas and concepts found in logic and reasoning. Thank you for joining us in this discussion, and we hope that you were enlightened by what we shared with you.
We hope that our discussion was able to give you a newfound perspective of logic and reasoning that is not founded on intimidation and confusion. This marks the end of your journey with us. We hope you had a fun time all throughout. See ya!